so sorry that I didn't get to come up there and be with you at the Green Bank facility. It's so beautiful and wonderful up there. But part of the presentation I'm giving today borrows some from the presentation we gave at the Western Conference, where our chief resident astronomer Mel Blake, Dr. Blake, shared some of the research that he and some of his undergrad students had been doing. And then I've got updates from a couple of our students, Brittany Ambrose and Ryan Frost, and they've been doing a good bit of the work on the project. And so we'll just move on along here. As you know, most of you know that SARA has sponsored our project to a degree, and we have some other sponsorships in the works. And our AIA Student Branch is sort of the focal point for our entire project. And at the upper right-hand corner, you see the logo of our new Bachelor of Aerospace Systems Management program. And in the ASM program, we're using the STEMSAT project as one of our experiential learning processes that we're going through, and that's working out really well. So basically, in a nutshell, STEMSAT is manifested for launch second quarter next year. And I have to say, based on our understanding of the process, that's probably a little optimistic, but we're not complaining, because every day we're coming up with something better and a little more advanced than what we had the day before. So more time is better, and it even enhances the student activity even more. But we're basically doing this as a STEM activity, or STEAM, if you want to put the arts in picture, where students are learning how to do lots of different science, technology, engineering, and math skills as part of the project. The secondary objective is the actual science experiment, which is a radio astronomy experiment to listen at VLF frequencies. We've chosen tentatively at least 20 kilohertz VLF, and those signals don't generally make it through the upper ionosphere. They're reflected back into space, so we don't get a lot of that coming through the atmosphere. So being above the atmosphere will allow our STEMSAT to receive that data and in some form, and I'll explain what we're tentatively planning, transmit that data back to Earth. And then, of course, we'll also be sending back some other data too. Looks like I went straight from the beginning to the end here. Hang on a second. So what is a CubeSat? Everybody knows by now they're a small satellite. The smallest size is a 4x4 inch cube, and weighs about 3 pounds. Currently, we're larger than that. The basic caveat for the CubeSats are they must be totally autonomous, have no major electrical interface and very little mechanical interface, minimized with the launch vehicle or any other payloads that might be aboard. As I said, we're scheduled to be launched in early 2024. Our orbit has been parameterized at 500 kilometers, basically a circular or near circular orbit with an inclination of 59 degrees, being launched out of Cape Canaveral Space Force Station. And we're not actually rebroadcasting the low frequency signals. We're converting those from analog to digital signals and basically sending back a flux reading, time-stamped and correlated with the satellite location and orientation. And there's some other possibilities we're working on. So that downlink will be at 434 megahertz, the 70 centimeter ham band, where that will penetrate. So as I mentioned earlier, our number one objective is to get children involved, K through 12 and higher, in things like mission planning, which we have class in our ASM program on that, and ground station operations, data reduction, correlation, hardware, software development, building, testing, launching, receiving signals, and working with the data. We're working with student groups all around the world to put together simple receiving stations that will be able to receive and record the data from STEMSAT and then send that data to Mel Blake over at University of North Alabama, where they're hopefully going to be able to correlate it and use it in a project that they have ongoing to do just that. The secondary objective is to get that flux data down. And finally, this objective secondary 2 is to send down the normal systems operational data, which will be like solar cell output, battery voltage, temperature, all kinds of little things like that. And we may even try to have a camera on board that doesn't point to the Earth, but points at some critical part of the satellite itself. That's being discussed. So who is our ride to space? Well, we've talked a little with you guys about that. It's VIA Space, which is a small upstart launch services company in Cocoa, Florida. They've been around for 10 to 15 years under different names, but they have changed to VIA Space as their banner. They are building a special rocket that's a hybrid propulsion vehicle that uses 3D printed fuel grains overwrapped with an epoxy, carbon epoxy sort of composite case, and use that inert high density polyethylene fuel with LOX, liquid oxygen oxidizer, to have rocket propulsion from that. It's to be built and tested in Cocoa, Florida. VIA Space is just completing one of their new facilities there. I visited them about 2 months ago now, and had some pictures and all from that trip. I should have put some of those in here, and I forgot to do that, but they're pretty far along in starting up their major engine project. I don't know if you can see my cursor or not, but the vehicle itself consists of this green tank. If you see my cursor moving, the largest tank at the bottom is the first stage oxidizer tank. And I think there's 8, maybe 6 to 8 strap-on fuel grains or boosters that get fed their oxidizer from that main tank. The second stage actually uses a similar motor as the first stage, but with a vacuum nozzle on it. And at the current time, there is no third stage envisioned in the basic Dauntless rocket. So this is it. And VIA has fired hundreds of hybrid rocket motors. They just haven't fired one as large or in the configuration that they're proposing for their launch system. And they're hoping to start wrapping a real test article of that size motor, maybe if not late this month, sometimes this fall, and start testing that probably late this year or early next year. And we have a launch pad assigned, which is pad 13, which is my lucky number for reasons that I'll tell you about sometimes if I ever get to come back to the to the Drake Lounge and participate in some of the funnery that goes on there. And we are anticipating that 500 kilometer orbit rather at 59 degrees. This is basically what the satellite looks like. This is sort of a crude cartoon of it, but the main functions are contained, of course, inside the 3-unit 4x4 by 12-inch roughly spacecraft structure. We have 4 deployable or fold out solar panels. We have a fold out UHF dipole antenna made from tape measure metal on the what we refer to the bottom end or the earth facing end of the satellite. And the receiving antenna is a relatively interesting design that we're working on, and it came about as basically as a packaging consideration as much as anything. But we're looking at a ferrite toroidal antenna, and we're basing that on some work that was done by the government several years ago. And I'll tell you more about this, but the Von Braun Astronomical Society, VBAS, in Huntsville has a relatively new radio astronomy group. And we have finally made the connection with them over the last month or so here, and great things are happening with our consolidation and collaboration with the radio astronomy group at VBAS, and they're helping test the antenna. As a matter of fact, they just completed about a 2-week testing of the ferrite toroid antenna recently. They're analyzing their data, but that's what the basic satellite looks like. The radio frequency spectrum we're looking at, of course, is the VLF range down in the submarine communications and beacon bandwidth. WWV has a beacon out of Colorado. There are many beacons around the world that transmit various information in this band. So we've picked a frequency that's not currently slated as an active transmitter at 20.1 kilohertz, although there's some very close to that. But it might be interesting to pick up a marker signal somewhere anyways to know that our receiver's working properly. But in the VLF range, home to natural electromagnetic emissions like spherics and tweaks and whistlers. And those of you who have played with Radio Jove data or the Inspire program, SID program, where we're listening to spherics and that sort of low frequency signals, know what this is, and it's basically called natural radio. But the right hand side of this chart shows that very low end of the radio spectrum anyways, that there's very little signal strength coming from space, next to nothing at that frequency. And we're talking about basically in the range of 10 megahertz and below. And when you get really down below that into the 20 kilohertz range, there's virtually nothing that makes it through. So there's a lot of interesting signals, we believe, coming from space, though, not only from the sun, which is going to be one of the dominant sources that we hear, but also from Jupiter and Io and lots of other things that we're hoping to capitalize on. You can see some of the opportunities here. Everything from plasma, magnetic fields, some of the high redshift things from the early history of the universe, solar bursts, planetary and exoplanetary emissions possibly, and lots of other things. And of course, our challenge is going to be to take the limited amount of data on STEMSAT 1 and make some sense out of it. So once we get the data, Mel and his people are going to be stuck with the job of determining what does it mean. So they have a hard job ahead of them. This is a chart that Mel and his student Harmony Wildharbour put together about Jupiter, and we're all pretty much familiar with that in our Project Jove activities, but certainly a strong signal when we're in the shadow of the sun anyways, we have a chance at hearing Jupiter and some of the other signals when we're in full view of the sun, we expect that it will be the totally dominant signal source and probably override or block out most anything else. And I've already mentioned solar flares, I think coronal mass ejections, high-speed solar wind streams, all these things that come from the sun are going to be extremely interesting to study. And I'm even considering going back to school again. Millersville University offers a graduate certificate in space weather. So I'm thinking about going for that. That is a very interesting field and certainly has big effects on our future and present times here on Earth. Here's some information borrowed out of our UK friends about solar flare classifications, highest being up there at the X class, going on down to A class. And I think when things are just sort of in idle mode, no big solar surface storms going or anything, we're A or B class. When things get really dicey, you might see some M and X class flares and such going on. And we've been going through that sort of pretty high activity over this summer. It's been really rough. If all of you who are ham operators know that, anything, the bands basically 80 meters and above have been just wrecked a lot this summer by all the solar activity going on. Mel and Harmony and some others looked at possible sources of domestic VLF interference, and we're hoping, the way we hope the satellite is going to be oriented, the receiving antenna is going to be facing away from Earth, whereas the transmitting antenna will hopefully face towards Earth. And the fact that most of this VLF signal source, we don't think is going to make it through the upper ionosphere of Earth, that it won't be as bad as it could be, but it could be bad. Things like mobile phones, and my goodness, we know how that is. Televisions are being less dominant these days. Computers are bad. Baby alarms, computer networking systems, this broadband system that we've heard so much about as interference sources for amateur radio, ADSL. Even these low energy light bulbs, the compact fluorescent light bulbs, are really a nasty thing. It seems like they're mostly going away to LEDs, but the LED light bulbs make a lot of noise too, as a matter of fact. So these are some things we're going to have to be aware of and figure out a way to minimize. Here's a picture that some of you haven't seen that basically gives a cutaway view of the pieces that go into our current prototype, which we have named the Engineering Model and Integration Aid. This is basically a full-up operating satellite, but with less than flight hardware quality components. And we're rebuilding the flight hardware using some of the funding we got from SARA and other sources. And we've got new printers to print a different type filament. We were using ABS. You see the red structure there is made out of ABS filament. We're now using carbon fiber impregnated nylon filament, which is much stronger, a little harder to print and keep your machine up and running. But I'm going to talk more about this very shortly, but the number one item there is our United Kingdom Radio Astronomy Association VLF receiver. And so they've developed this receiver over the last decade, or maybe a little longer, for receiving terrestrial based spherics and that sort of thing. And one of the things that we liked about it was that it has a form factor that can be modified to fit in our CubeSat. It's really mostly through hole parts, so our students all can build it fairly easily. And we basically, the blue board you see there is based on one of the UK RAA kits that we built using a cut down version of the board. We actually took their stock circuit board and trimmed it down as much as we could and made it fit in the satellite. Since then, we have redesigned the board to fit perfectly with our other boards. We've yet to have any of those produced. It's still sort of in the engineering checkout stage to make sure we haven't messed it up. And it's like almost in every other circuit board I've seen, something may slip through and we may have more than one iteration of it. But so that's the receiver that feeds. One of the other things we like about it, it has a built-in A to D converter and some RAM in it and lots of other little things that make it ideal for a simplified project like we're trying to do. And I'll show you a block diagram here shortly. But then the aluminum colored thing there with the white little boxes on top, that's our lithium ion battery. It's a 10 amp hour battery pack, which is larger than most CubeSats that you see. The item number 7 is actually a 2 to 3 watt UHF amplifier that will take the RF signal that's modulated with data and transmitted based on it's basically a computer generated signal. The Raspberry Pi on board our control board is generating the RF. So we drive our RF amplifier with that. And so preliminary tests look good. Not too many spurious emissions from it. It's all looking really good. And then our homemade solar panels made on a PC board substrate that you see there, 9A and 9B, front and back of those. Those are spring hinged and they fold out along with the little antenna on the board below. Here is the block diagram, and this is very elementary and not a lot of detail here, but you can see the simplicity really of what we're trying to do. And I believe I've mentioned before that we are not reinventing the wheel like most people do, are spending a lot of money on prefabbed or CubeSat subsystems that are available. I know our friends up in Knoxville area spent so far probably over $30,000 on their little satellite, and so far we have less than $10,000 invested in everything we've done, so we're not too bad off. But anyway, so going from left to right, we've basically got the toroidal antenna that picks up the VLF, sends the signal to the UKRAA VLF receiver. It does its receiving thing, converts the analog signal strength. It's basically a flux reading. It converts that to a digital signal, timestamps it, and sends it to the payload board, which is a board that interfaces various types of sensors to our control board, which is the next thing to the right. And Arduino, a little Arduino, is doing all the computer magic to interface the various sensors. We've got temperature, humidity, pressure. We're going to maybe have a camera. We'll have the receiver. We're looking at putting an inertial measurement unit module in that, and also a GPS, all on that experiment board. And so that data will go to the board, and the experiment board and the control board are stock boards from AMSAT. They're not fancy, they're not very capable, but they do the job for what we're trying to do on this first satellite. So those are available, and it's run by a Pi Zero, I believe. At least it's a Raspberry Pi. I'm pretty sure it's a Pi Zero. And then it generates the RF signal for the downlink, and we send it to our amplifier over there. And finally, it goes to the 70 centimeter dipole. And the one of the biggest things that we're developing is the timer and control board that will monitor the status of the CubeSat in its canister. And once it is deployed by the rideshare vehicle, the Dauntless rocket, it will set a timer, 5-minute timer, that after that elapsed time will burn a wire, a nichrome wire that holds the hinged solar panels with the folded dipole antenna under them. It will burn that and allow those things to spring open and deploy, and it will also turn on the basic satellite power systems. It'll be kind of in a sleep mode until then, but we'll start transmitting data immediately once that 5-minute time has elapsed. The control board, by the way, does have individual solar panel voltage and current controllers on it, and it will send a charging signal down to the big battery pack based on what it gets from the 4 solar panels. We also have a burn wire battery pack that's separate from the system rail, overall system power rail, and it will be about, I guess it's going to be 4 lithium 16850s or 18650s, whichever it is. I think it's 18650 batteries, whose sole purpose will be burning the wire, because that takes a lot of amperage and there's some room for problems with that, and we don't want that kind of activity on our main power bus. So we got a little battery pack separate for that activity. And so the software that runs all of this is going to be a modified version of the AMSAT CubeSim software, which you can download from AMSAT and play with that. We've built 2 or 3 of the overall AMSAT CubeSat sims, and so we're going to adapt that software to our mission, and it's very easy to do. And again, that's takes a lot of development time and expertise to do that. So by going with something that's on the shelf and is being improved all the time, Alan Johnson, you all have probably heard of him. He is one of the main CubeSat gurus at AMSAT. He has developed the CubeSat sim activity for STEM and STEAM activities. And he's about to come out with a new group of boards that run off of a different lower cost processor. The little Raspberry Pis and such that this thing was originally designed around used to be $15 or $25. Now they've surged over $100 a piece. I think they've come back down though, and availability is improved. But we're going to look into what Alan's new version looks like too. So anyway, that's the block diagram. Nothing real fancy, pretty simple. Here is the receiver itself, and as you can see, this is old-fashioned electronics here for the most part. I think there's 1 or 2 surface mount parts on here, and the rest of it is something that we can put a 8th grader on to build, basically with a little basic soldering skills. But it has a pretty good capability. And for any of you who are interested in knowing more about that, you can go to the ukraa.org, I believe it is, website, and you can buy one of these, and they have a beautiful receiver manual that goes with it, and also a very well done construction manual, a little separate 15 or so page construction manual. A lot of good things going on there. It has more capability on this board than we're probably going to use. It has I2C output. It has the A to D converter output. It's just got lots of things going for it. And it's not very expensive. I think the rough kit form receiver here is about $100. So it's not that bad, and it filled the gap. We researched everything from building a receiver from scratch, and of course, SARA has been through that exercise before. We also looked at a existing atomic clock receiver down in this frequency band, and just looked like it was going to be too difficult to modify that to do what we wanted to. So we ran across this option, and so far it's might be the thing. But we got the VBAS people looking into how we can further enhance the data gathering and transmitting capabilities by making this a scanner of sorts that will look at a range of frequencies rather than just be locked onto one single 20.1 kilohertz frequency. We might scan a range of frequencies with a time code in it to make sure we knew what was what. Has a pretty decent bandwidth here. You're looking at some data from the UK RAA group, and this receiver here is tuned at 23.4 kilohertz, and you can tune this receiver depending on which frequency you want to receive, and this is the kind of bandwidth response you can get out of it. This is the sensitivity of it, and it's not bad for what it is. So like I say, the Von Braun astronomy group with the radio astronomy special interest group is researching that. We're also building our own canister and ejection system from the rocket. We're not going to be using the regular P pod that most people use. These things are very expensive, and you have to meet a very rigorous specification to fit into this thing and to utilize it. And it was our launch provider that said, hey, you guys build your own dispenser. Tell us what it looks like and we'll put it on the rocket. So that's what we're doing, and it's interesting, but it's kind of fun in a way. There is a new RFP out. Some of you may have already seen it. If some of you would like to get into this business of CubeSats, Firefly Aerospace just issued a new RFP. It's the Dream 2.0 RFP release that are looking for 12 to 24 month down the road CubeSat projects as possible rideshare candidates. So we might propose on that for a STEMSAT 2 activity. One of the things that's different from what we're doing, though, they require that you must fly your spacecraft in a space qualified dispenser. Now, whether or not we can consider our dispenser space qualified if we have a successful launch on our first satellite is another issue, but not likely. But anyways, that's what it looks like. And this is kind of a crude drawing, but it's basically a loaf of bread sized box with a spring door on one end and an ejection spring on the other end, and a nichrome burn wire holding the door shut until such time as, in this case, the burn wire on the canister or the dispenser is, that signal is sent from the rocket, from the launch system control to burn the wire and release the STEMSAT. And when it's burned, the door opens and the spring behind it pushes the satellite into space, waits 5 minutes, wakes up, burns the wire, opens the solar panels and deploys the antennas, and hopefully comes to life. And we are going to be testing all of that at ADTRAN and Dynetics. I think I mentioned to you guys before, one of our contacts at Dynetics, Steve Mustakas here in the Huntsville area, passed away unexpected recently, a very young man in his early 50s. He died of AFib, basically, after having an incident on the soccer field. So that was not a good deal. He's wonderful, wonderful gentleman, had two young teenage boys. They built a home-built airplane together. He was just in the prime of life. Such a terrible loss. So to recap things, as we've been saying for the last 6 to 7 years, CubeSats offer a unique opportunity to expand our hobby. Amateur radio astronomy in space opens up a whole new realm of possibilities for everyone, I think, and on each end of the spectrum, whether you're receiving, transmitting, doing scientific research, just learning how to track and recover satellite data, any of that. And in this mission here, the signals that we hope to hear have basically not been heard much from previously, certainly not by amateur satellites. And so we may have a lot of data to analyze. The time-stamped measurements will also give us the satellite orientation, timing, the flux level of the signal, and if we decide to do the scanner, the frequency and flux level of the signal. And if you haven't caught on to this yet, this is an autonomous satellite. STEMSAT 1 does not have uplink capability. We decided to make it as simple as we possibly could, and that cut out about half the problem, or at least in our view it did. So STEMSAT 1 is strictly operating in beacon mode. We're looking at the STEMSAT 2 possibilities in the future to be a full uplink, downlink, controllable satellite, even attitude control, that kind of thing, but that would be several more years down the road. And we're hoping to launch next year. Just let me say next year. I will be pleasantly surprised. And as I just mentioned, we are reviewing the Firefly Aerospace Dream 2.0 RFP and considering submitting a proposal for that if we can force ourselves to get over the fact that we have to redo everything to fit the P-pod. The P-pod is not that different from our canister, except in terms of cost. It's probably 100 times more expensive than what we're making, so it would be certainly a big investment. Guess where this is? Where I would like to be right now, Green Bank. And again, thank you guys for the opportunity to present, and my students and myself are so sad. Everybody had a viable reason for not being there. The week before, last week, I got into some interesting health issues that I have not been able to do much traveling at all, even locally lately, but I'm much better. Things are going to be fine. And we do have a young lady who's a student at Athens State from South Africa. She's going to be heading up our South Africa tracking team and STEM students near Johannesburg, I believe. Her name is Rosalind Daka. She's going to be doing a presentation tomorrow on the square kilometer array, just as a real top level descriptive sort of thing. And this is one of our t-shirt logo from one of our supporting institutions down in Central Alabama. This is Central Alabama Community College t-shirt logo for STEMSAT Project. And they have a very active student support services group that does STEM work. And they've already started building their own CubeSat sim, and they're fired up and got their tracking station already built and online. So they're quite a group. Jeremy Carr is one of the instructors who's leading the group down there. So with that, that's pretty much the end of the show. So I will turn it over to the powers to be to allow any questions. I know we've got the program director listening in. Brandy Wheeler is our STEMSAT project director. She's online, or at least was a few minutes ago, and I'm not sure if if the others were able to show up or not. But be sure to tune in tomorrow to hear Rosalind talk about the SKA.
Well, an excellent presentation, Wayne. Thank you so very much. It's really inspiring. We do have an online question from Deanna, and she's asking, what is the expected operational lifetime? And will watchdog timers be implemented for automated recovery from unexpected failure?
Okay, we are basically planning on a 500-kilometer circular orbit. And at that altitude, we could survive up to 2 years, possibly, depending upon solar activity. This is a solar max period that we're in right now. So drag will be increased by all of the particle activity in the atmosphere. So we're not really sure. As a matter of fact, we're searching for someone who could make an estimate of that. And while we are discussing the possibilities of doing a directed dive back to Earth once STEMSAT 1 might die, we haven't incorporated any subsystem in the satellite to do that. In terms of recovery from an failure on orbit, we are looking into that, and that's probably the biggest area where our software is going to have to be upgraded from what we're getting from AMSAT. We're going to have to make redundancy more built into it. We're going to have to try to overcome latch ups and upsets and that sort of thing caused by radiation. And so we're looking into that. And so we are looking, if anyone in the group here is interested in supporting that software development effort, we'd certainly like to hear from you. But so far, those issues haven't been settled, Deanna, and I appreciate the question, a very good one and a very important one to be addressed.
Okay, do we have any questions here at Green Bank? Nobody's raising hand. How about online? Anybody want to speak up or post in chat?
Yeah, I've got a question, Wayne. The toroidal antenna, normally we're using toroids to keep it from radiating magnetic fields.
Yeah,
it would make it less sensitive being a toroidal pickup antenna. Normally the VLF antennas are rod-shaped spheroid antennas.
exactly. And that is a question that we are investigating with the VBAS people. We picked that design after looking at various configurations of ferrite rod antennas. We basically did some experiments with the atomic clock rod antennas down at this frequency range, and they do work probably a little better than the toroid, but it's a little more complicated. The form factor on the toroid is perfect for what we're wanting to do with it. And I think we're going to be pleasantly surprised by the data that VBAS has collected. We were comparing the signal strength, the received signal strength from this little, basically a 4-inch diameter toroid antenna with a 3-foot, it was a meter square, 100 meters, I think it was 100 meters of wire loop antenna at the VBAS facility. And while it was noticeably degraded from that big, huge loop antenna, we still had a usable signal. So it's under consideration, and you make a really good point. There is a report I'd be glad to send you the link on. Of all people, the CIA did a very intensive study on toroidal antennas for covert, I guess, and other types of work. And it turns out they're pretty decent if you take certain things into consideration. But yeah, you're right. You say the obvious. Most people, particularly ham operators, think of a toroid as a transformer of some sort or a noise suppressor device that does exactly what you say, but it will work as an antenna.
And you're also up in the orbital plane, well, just below where all the Starlink satellites are. So let's hope they have quiet DC-DC converters.
Well, there's no telling what we're going to receive or what we're going to be able to make of it once we get it. But I think this first mission is going to be sort of an exploratory mission of what can we really expect to get out of a spacecraft like this, and what measures on STEMSAT 2 could we take to make it better. So this is going to really be a learning experience for all of us in many different ways. So you make excellent points, and hopefully we'll learn something from the experience.
Is there any other data that shows what kind of signal strengths you could be receiving up there? You wouldn't want to completely saturate the receiver if you knew it ahead of time.
I don't have any information with me right now, but again, that's something that we're looking into with the VBAS people, and probably the next time we have a summary report for the group, I'll have some data along those lines that I can share. But yes, and Mel and his people have been looking into that sort of thing too, exactly what we can expect in a way of signal sources and signal amplitudes and so forth. So it's still under study.